Lesson number 6, stretches. Today we're going to be looking at the third type of transformation, which is stretches. So we're going to look at vertical and horizontal stretches. First, vertical stretches. As you guessed it, vertical stretches are going to affect the y value. So you know that when we added to the y value or subtracted to the y value that we moved up or down. And when we made the y value negative, we reflect it over the x-axis. So now we have a third thing that we can do, and it is going to be by multiplying the y. So we are going to consider the function y equals f of x equals the square root of 4 minus x squared. I have started by graphing this function. So go ahead, do the same. Here is y equals the square root of 4 minus x squared. Now if we have to match that up to our graph that I have in your notes, that is going to be equivalent to the red. Okay, I can tell that because on my TI-83, I can see that the y-intercept is 2. From there, we are going to make two different equations. We are going to take 3 times f of x, and we are also going to take 1/2 times. So let's think about that in terms of our equation. So if we take our equation, square root of 4 minus x squared, and we multiply that function by 3, and we get y equals 3 times 4 minus x squared. Now, because the 3 is not directly attached to the x, we know this has to be affecting a y value. So to see just how it is affecting the y value, let's move the 3 to the other side. So remember, another way to write y over 3, 1 over 3 multiplied by y. And then on the right-hand side, we just have 4 minus x squared under the radical symbol. So this equation, now you can see what we had to replace y with. We had to replace y with 1 over 3. So the replacement notation would be y is equal to 1 over 3y. Now let's check to see what that looks like when we graph that original equation. So think back to when I'm graphing it, I'm going to put in what I originally came up with as my equation, which was y equals 3 times the square root of 4 minus x squared. We have to put things in the form y equals in order to put them in our calculator. Okay, so go back to my y editor. I'm going to leave my original function in there, and then I'm going to take 3 and multiply it by the square root of 4 minus x squared. Okay, let's see if it's going to be the green or the blue graph. Ah, look at that. It is the green graph. So what that means is that when I take y and I replace it with 1 over 3y, I get, I'm just switching my color of my pen here, I get a vertical stretch. Therefore, vertical stretch by a factor of 3. Okay, so we have taken the original red graph and stretched it vertically by a factor of 3. So notice how that plays into our mapping, our replacement notation. 1 over 3y gave us a vertical stretch of 3. So it's the reciprocal of that number. Okay, let's go ahead. I think that we can recognize now that the next graph is going to be the blue one. But let's go ahead and write it out. Okay, so writing it out, we now have y equals 1/2 times our function. So this is once again what I'm going to graph to get the blue graph, and I'm not going to do it this time because I think we can already see what we're going to get. But I'm going to do the same thing by multiplying both sides by 2 in order to get the 2 to the other side of the equation. The 1/2 times 2 cancel each other out, so I'm left with 4, the square root of 4 minus x squared equals 2y. So now I can see that my notation, my replacement notation is y is replaced with 2y, which causes it to have a vertical stretch still, but now the vertical stretch is by a factor of 1/2. So anytime we have a number less than 1, it means it's going to basically like squish it down rather than expanding it. Vertical stretch by a factor of 1/2. So notice, once again, it's the reciprocal of the number that we replaced it. You'll probably start to see the pattern that a lot of these are the opposite of what actually. Let's look at horizontal stretches. So horizontal stretches, just like translations moving horizontally, are going to affect the x value. And they are going to multiply the x value. So we're going to use that same function, the square root of 4 minus x squared. We already know that that was the red one. And then we are going to do two things to it. We are going to take the 4 and multiply it by, we're going to take the x and map it to 4x. And we are going to take the x and map it to 1 over 3. So once again, let's write both of those equations out. For the first one, we have y equals the square root of 4 minus, with my bracket placement here, 4x needs to be in brackets, squared. Expanding that just a little bit, we have y equals 4 minus 16x squared. I'm going to take a second to graph it. The square root of 4 minus 16x squared. Good. Okay, let's check, see if it's the blue one or the green one. There's my original function, the red one. And there's my TI-83 doing its best job to graph that blue function. So we have created a horizontal stretch by a factor of a quarter. So when we map x to 4x, we are doing a horizontal stretch by a factor of a quarter. So essentially we're squishing the graph when that is smaller than 1. So one thing that I forgot to mention on the previous piece of the notes is this wording. When I say horizontal stretch by a factor of a quarter, that's very important. But it's also important that I say about the y-axis. So that is the basics for where we stretch it. You'll notice once again our invariant points are on the y-axis, and we're stretching it on either side of the y-axis. Okay, let's create our green equation. I have x mapping to 1 over 3x, so when I place that into my equation, I will have y equals the square root of 4 minus 1 over 3 x squared. Y equals the square root of 4 minus 1 over 9x. When you graph that, you will get the green graph, which you can see has been stretched by a factor of 3. So it is a horizontal stretch by a factor of 3 about the y-axis. Just take a brief second to see how that relates to our replacement notation. The blue graph, we replaced it x with 4x, and we got a stretch by a factor of a quarter. And then the green graph, we replaced x with 1 over 3x, and then we got a horizontal stretch by a factor of 3. So same pattern as before, we are going to flip it to get what our horizontal or vertical stretch is. So let's summarize here. The first one, we are changing the a value in y equals a times f of x, which means we are directly replacing y. And if we move that y over to the other side, we're replacing y with 1 over a y. So if we replace y with 1 over a y, we are going to get a vertical stretch about the x-axis by a factor of a, the reciprocal of whatever you replaced it with. For our mapping notation, it is going to stay similar to how it did with our translations, which means that it's the opposite of our replacement notation. So our x is going to stay the same. Our y is going to be multiplied by a. Okay, let's look at the horizontal stretches now. So here we have y equals f of bx, which means we are taking x and replacing it with bx. So if we replace x with bx, the graph of y equals f of x is going to be horizontally stretched about the y-axis by a factor of 1 over. And for our mapping notation, our y value is going to stay the same, but our x value is going to have to be multiplied by 1 over b. So once again, opposite of our replacement notation. Okay, let's try it. Let's see if we can do a couple examples here. Given the graph of y equals f of x, sketch the graph of y equals f of 2x. So we're given our original function and we're asked to create a new function. Now always ask yourself, what has changed? So x was replaced with 2x. If x was replaced with 2x, I know that we are dealing with a horizontal stretch. So therefore, we have made a horizontal stretch about the y-axis by a factor of, and if we put 2x in there, then it means it's going to be by a factor of 1. So what that means in terms of our graph is all the points on our y-axis, they stay on our y-axis. They cannot get stretched horizontally. But the rest of the points, they are going to get stretched by a factor of 1/2. So we take the x value, say for this one, -4, and we are going to multiply it 1/2, and our new point is going to be at -2 and 2. Okay, the point on the x-axis, -6, 0, is once again going to be multiplied by 1/2, and it is going to move to -3, 0. Notice that my y values are not changing, only my x values. Okay, this point here is my invariant point at 0, 4. My point at 4, 0 here is going to be multiplied by 1/2 to give us 2, 4. And then I have 5 is going to come to 2.5. And 6 is 3. So once you have plotted your points, go ahead and connect them. The blue line is my completed graph of y equals f of 2x. We have taken it and stretched it horizontally about the y-axis by a factor of 1/2. Let's try the next one. State the equation of the image of y equals f of x. After a horizontal stretch by a factor of 1/2 about the y-axis, and a vertical stretch by a factor of 3/7 about the x-axis. So if we are making an equation, I recommend doing replacement notation. I have 2 replacement notations to use here. I have to replace x and y. So the horizontal stretch by a factor of 1/2 means that x is going to get mapped to or sorry, not mapped. X is going to get replaced with 2x. The vertical stretch, y, is going to be replaced with, and it says by a factor of 3/7 about the x-axis. We flip it to be by a 7/3x. Is how it's going to get replaced in the equation. Sorry, that's supposed to be a y. 7/3y. We are not replacing y with x. Okay, so x gets replaced with 2x, y gets replaced with 7/3y. Now let's take our replacement notation and put it into our equation. We have 7 7/3y equals f of 2x. So we've taken that original function and replaced y with 7/3, y, and x with 2x. Now let's isolate for y. To get the 7/3 to the other side, we multiply both sides by 3/7. That causes the left-hand side to just have a y because the 7/3 times 3/7 multiplies to 1. And on the right-hand side, we have 3/7 times f of 2x. That is our equation to get the following stretches. Next example. State the equation of the image of y equals x squared after a horizontal stretch about the y-axis by a factor of 3/4. These ones are nice if they give us equations because we can use our calculators to check our answers. So we have the original graph y equals x squared, and we have a horizontal stretch by a factor of 3 over 4. So if it's a horizontal stretch, that means it's a change in x value. Our x is going to get replaced with 4 over 3x. Now we take that and we put it into our equation for x. And remember, always, always, always replace things in brackets. It's going to be key for this one. So we get y equals 4 over 3x, the power of 2. 4 over 3 squared is 16 over 9. Okay, I'm going to graph it now. I have typed x squared into y1, and I typed my new equation into y2. And now I will check to make sure that it actually is indeed a horizontal stretch by a factor of 3 over 4. So I'm just going to zoom standard. So there's x squared, and there is my new function. So I can see, remember 3 over 4 means it should be slightly narrower, and that's exactly what has happened. So I have likely done it correctly. Okay, next example. Let me box up my answer for the previous question. That is my new image. Describe how the graph of 3y equals f of x can be obtained from the graph y equals f of x. Once again, I like to use that replacement notation. We're starting with y, and the y was changed to 3y. So if y was replaced with 3y, that means that we have a vertical stretch by a factor of 1 over 3, about the x. So remember when it says describe, that's a math directing word, and it means use your words to explain what's going on. So this here of saying that it's had a vertical stretch by a factor of 1 over 3 about the x-axis is what the question is asking for. Next example. Describe what happens to the graph y equals f of x with the mapping of x comma y produces 8x comma y. So there are many different ways that you can attempt a question like this. I'm sure, knowing the brains in the room, we could come up with lots of different ways. I'm going to stick to the standard of flipping it to replacement notation, which in turn can tell us exactly what's happening to the graph. However, even if you just want to look at that and say, okay, well, that means the x value is going to be stretched by a factor of 8, that is also acceptable. So to get 8x as our mapping notation, we know that our original function, our equation would be substituted with 1 over 8x. And this tells us that we have a horizontal stretch about the y-axis. We are getting used to this phrasing by a factor of 8. So if our x-coordinate is multiplied by 8, it's going to get 8 times larger. So it's going to be a horizontal stretch about the y-axis by a factor. Describe, next example, describe using mapping notation. So remember mapping notation, that's the x comma y. how the graph y equals 4 times 2 to the power of 3x can be obtained from the graph y equals 2 to the power of x. So we'll get into this later, but this is an exponential function. We actually have a whole unit on it later when x is a variable, but we can still apply our knowledge to see what has happened. So the first thing I notice is that the x has been replaced with 3x. So that tells me right away, I know that we have had to have a horizontal stretch. So it's a horizontal stretch. My pen's not working very well, so I decided to just type it out, but it's a horizontal stretch about the y-axis by a factor of 1 over 3. Okay, now we have to figure out where this 4 is coming from. We know it's not directly attached to the 3x. So right away, we know it's not affecting x. However, if I were to divide both sides by 4, we would get y over 4 equals 2 to the power of 3x. That means that y is being mapped to 1 over 4y. That helps us find what kind of stretch is happening. So once again, I'm just going to. So therefore, we have a vertical stretch about the x-axis by a factor of 4. So this one, once again, could be checked using your calculator. We have a horizontal stretch about the y-axis by a factor of 1 over 3, and a vertical stretch about the x-axis by a factor. Time for the last example. Now we have a graph. Given the thin line graph of the original function, we're actually given the function. Is x plus 4 times x minus 2 times x minus 6. We will see functions like this in our polynomial unit. Determine the equation of the stretched thick line. Thin line is our original, and the thick line is the new one. So the first thing I notice is that my maximum on this graph and my minimum on this graph, if I were to point those out, have not changed values as far as our y values go. That's telling me that likely we're not seeing any type of vertical stretch. We're only seeing a horizontal. So now I'm going to check to see, well, by how much? So I can see my x-intercept started at -4 and it moved to 8, or sorry, -8. So that likely means that we are multiplying by a factor of 2. So we are going to have a horizontal stretch by a factor of 2. Okay, so we have a horizontal stretch by a factor of 2 about the y-axis. As far as our replacement notation, it is going to be x map. X is replaced with 1 over 2x. So all of the x's are going to be replaced with 1 over 2x. And since my pen's not working very well, I'm going to finish this example up on Monday because it's a little heavy on the algebra. However, I did just realize that I didn't fully answer the last question. So the last question wasn't asking me to describe using words. It said describe using mapping notation. So my mapping notation of x, comma y, and it looks as though my x needs to be multiplied by 1 over 3x, and my y needs to be multiplied by 4. So it's the reciprocal of whatever we use in the replacement notation. So So we will finish up the last example on Monday.